Imagine for a moment a colossal entity drifting in the quiet void of space, not emitting light, not drawing attention to itself, but quietly exerting a gravitational force so powerful that it bends the very fabric of reality around it. This is not science fiction. It is a silent cosmic giant, a black hole. But not just any black hole, one so massive that it weighs an astonishing 400 million times more than our sun. Despite this unimaginable mass, it doesn't blaze with light, doesn't scream through space with X-ray radiation like many others do, it doesn't roar, it hides. This remarkable discovery, made possible through the advanced capabilities of the James Webb Space Telescope, has forced scientists to rethink what they thought they knew about the early universe. It's not simply a new data point. It's a paradigm shift. A cosmic rulebook, long taken for granted, is now being revised. The telescope's observations have revealed something previously thought unlikely, a massive, dormant black hole from the universe's infancy. But how was it found, and why is it so significant? The Webb telescope, equipped with powerful infrared instruments, was able to peer deep into the ancient universe, into a time less than 1 billion years after the Big Bang, in one of the galaxies. From this early era, scientists detected something extraordinary. At the heart of this young, still-forming galaxy lay compelling evidence of a sleeping black hole, one that challenges our current models of how such objects form and evolve. This black hole wasn't radiating energy. It wasn't surrounded by a glowing accretion disk, nor was it actively feeding on nearby gas and dust. It gave off almost no direct signal, so how did astronomers know it was there? They analyzed the movement of stars within the galaxy. The light from those stars told a story, one of disruption and extreme gravitational influence. The stars were moving at speeds and in patterns that could only be caused by the pull of a massive, invisible object. This motion acted like a cosmic fingerprint, unmistakably pointing to a black hole hidden in plain sight. The implications are enormous. A black hole of this size in such an early galaxy is more than just a curiosity. It's a challenge to the prevailing understanding of how black holes grow over time. Typically, black holes form from the remnants of massive stars and gradually gain mass by pulling in surrounding matter. It was believed that in the early universe, such growth would have been slow due to limited material and time. Yet, this black hole had already reached a mass of 400 million suns, and it had done so less than 1 billion years after time itself began. To help illustrate just how massive this object is, if the sun were the size of a ping-pong ball, this black hole would be comparable in size to an entire city block. Even more striking is its proportion relative to the galaxy it resides in. This black hole makes up nearly 40% of its host galaxy's total mass. In today's universe, supermassive black holes typically account for only about 0.1% of their galaxy's mass, a tiny fraction by comparison. The imbalance here is staggering and demands an explanation. How could something so heavy have formed so quickly and dominate its environment so completely? This finding suggests that something very different was happening in the early universe. One possibility is that black holes formed first, perhaps from the direct collapse of massive clouds of primordial gas. If this theory is correct, black holes didn't wait for stars and galaxies to form. They came first and galaxies developed around them. In that case, black holes were not just passengers in the cosmic story, they were architects. They may have served as gravitational anchors, pulling in material and shaping galaxies from the inside out. Alternatively, this black hole could have experienced a phase of super-Eddington accretion. This refers to a situation where a black hole consumes matter at a rate far exceeding what traditional physics predicts is sustainable. During such a feeding frenzy, it would grow rapidly, devouring gas, dust, and other materials at up to 10, 20, or even 100 times the expected rate. Eventually, it would enter a dormant phase, like the one we're witnessing now, having already consumed most of the available matter in its vicinity. There's also the intriguing possibility of direct collapse black holes, which may skip the usual process of star formation and supernova explosions entirely. In this model, massive gas clouds in the early universe could have collapsed directly under their own gravity into enormous black holes, bypassing the intermediate steps. These objects would be born not from stellar deaths, but from cosmic chaos, forming millions of times the mass of the Sun almost instantly. If this idea holds up, it forces us to rethink not only black hole evolution, but also the broader history of cosmic structure. Perhaps galaxies are not the birthing grounds of black holes, but rather the remnants of their gravitational influence. What makes this discovery even more fascinating is that it may be only the beginning. Dormant black holes like this one are exceptionally difficult to detect because they are not actively feeding. They don't emit the bright X-rays or energetic radiation that usually makes black holes visible to our instruments. They don't light up the sky, instead they lurk in darkness, quietly shaping the galaxies around them. The fact that Webb was able to identify one means there may be many more, possibly even countless others, silently influencing the structure and evolution of galaxies across the universe. The consequences go far beyond black holes themselves. This discovery touches on nearly every major question in cosmology: how galaxies form and grow, how stars are born and distributed, and even how mysterious forces like dark matter and dark energy operate on grand scales. If black holes can exist independently and guide the growth of galaxies, then they are not merely outcomes of cosmic evolution. They may be central drivers of it. It's also important to compare this black hole to other recent discoveries. For instance, the Gaia mission uncovered Gaia BH3, a dormant black hole with a mass of about 33 times that of the Sun. While that is notable, Gaia BH3 is located in the relatively nearby modern universe and is much smaller by comparison. The black hole detected by Webb, on the other hand, is ancient, immense, and represents a completely different category. It existed when the universe was still wild, chaotic, and unstructured, a time when the first galaxies were just beginning to emerge from the cosmic darkness. This leads to an eerie and profound question: how many more of these silent titans are still out there, hidden from view? What else lies undiscovered in the darkest, most distant corners of the cosmos? Each observation made by the James Webb Space Telescope peels back another layer of the universe's hidden history. And this discovery is a powerful reminder that the most significant forces in the cosmos are often not those that blaze brightly, but those that quietly shape everything around them. The universe continues to surprise and astonish. Just when we think we've begun to understand its patterns and rules, discoveries like this one remind us that our knowledge is still incomplete. We are still in the early stages of a long cosmic journey, one that reveals just how mysterious, unpredictable, and awe-inspiring the universe truly is.